Today we are going to be talking about a technology called hydrogen blending. We will discuss how it works and its potential environmental impact. Hydrogen blending is the addition of hydrogen gas into natural gas. Hydrogen is created through electrolysis using excess power from the grid. The hydrogen gas can either be directly injected into the natural gas line or stored. The stored hydrogen can either be injected into the natural gas line at a later time or converted back into electricity in a fuel cell. The increased concentration of hydrogen in the natural gas provides a lower carbon fuel. Given the current natural gas infrastructure in Canada, this technology could be widely implemented and is a step towards carbon emission reductions. The first step in the process is the generation of hydrogen through electrolysis. Since the covalent bonds in the water need to be broken to allow the hydrogen and oxygen gases to form, energy is required. From the specific enthalpy of each bond, it can be showed that 498 kilojoules of energy is required. This energy requirement could be fulfilled by renewables operated during non-peak hours. As per the Renewable and Sustainable Energy Review from Science Direct, a concentration of about 10% hydrogen could be injected into the existing natural gas grid with no detrimental effects to the infrastructure. A 10% mixture by volume of hydrogen and natural gas, assuming a temperature and pressure of 25 degrees Celsius and 200 psi, would consist of 2 moles of hydrogen and 9 moles of CH4. The hydrogen and natural gas blend can be transported as a fuel to the end user. When the gas mixture reaches the end user, the following two combustion equations occur. The 2 moles of hydrogen are oxidized to produce water, 498 kilojoules of energy. The 9 moles of natural gas is combined with oxygen to produce water, 9 moles of CO2, and 7,218 kilojoules of energy. The total heat energy provided to the end user would be 7,716 kilojoules. The carbon emissions is 9 moles of carbon dioxide. Currently, end users are using pure natural gas as their fuel source. In order to receive the same amount of energy, but with pure natural gas, additional moles of CH4 is required. This would result in 9.6 moles of CO2 emissions instead of 9. These can be converted back into their respective carbon intensities by finding the mass of carbon dioxide emitted per kilojoule of energy required. Based on this calculation, the carbon dioxide emissions can be reduced by 6.2% with the usage of hydrogen blending. As Canada already has a large network of natural gas pipelines in place, as seen in the picture, it would be not significant cost to implement hydrogen injection. To explain what kind of impact the injection of hydrogen would have, use Canada's example. Canada is the 4th largest producer of natural gas in the world at 0.5 billion cubic meters per day, and 69% which was produced in Alberta alone. Continuing with our Canadian example, industry used 1,348 petajoules, or 53% of the total natural gas consumption in Canada for 2016. Using a carbon intensity of 56.1 kilograms of CO2 per gigajoules for pure natural gas, 1.348 times 10 to the 9 gigajoules, or 1,348 petajoules, the carbon footprint of Canadian industry from natural gas emissions alone in 2016 was 7.56 times 10 to the 10 kilograms of CO2. Using the previously determined CO2 reduction of 6%, we can get a total emissions of 7.11 times 10 to the 10 kilograms per CO2, or a reduction in emissions of 4.5 times 10 to the 9 kilograms of CO2. As a reference, assuming the standard car in Canada drives 15,000 kilometers a year with a fuel consumption of 10.7 liters per 100 kilometers, and 1 liter of gas is equivalent to 2.29 kilograms of CO2, the carbon reduction is equivalent to 1,208,200 cars off the road in Canada in 1 year. Based on the promising carbon reduction potential of hydrogen blending, several jurisdictions currently have hydrogen blending projects in various stages. Much like all storage system, the purpose of hydrogen blending is to redistribute excess power to match future demand. For example, PV produces energy at midday when demand is typically low. This energy can be used to power the electrolysis, resulting in a cleaner burning fuel source for the end user.